Hello everyone, my name is V. Pansai Srinivas from CSIT B section. My roll number is C7. Today's my tech talk topic is schur complements of Z matrix. Subject linear algebra and calculus. What is Z matrix? The class of Z matrix are those matrices whose off diagonal enters are less than or equals to 0. That means Z is equals to Zij, where Zij is less than or equals to 0, where I is not equals to j. A Z matrix is a square matrix of the form lambda I minus A, where lambda is real and A is an element-wise non-negative matrix. What is schur complement of matrix? Suppose p, q are non-negative integers and suppose a, b, c, d are respectively p cross p, p cross q, q cross p and q cross q matrices of complex numbers. Let m is equals to a, b, c, d so that m is a p plus q cross p plus q matrix. If D is invertible, then schur complement of the block D of the matrix M is the P cross P matrix defined by M by D is equals to A minus B D inverse C. If A is invertible, the schur complement of block A of the matrix M is the Q cross Q matrix defined by M by A is equals to D minus A inverse B. In the case that A or D is singular, substituting a generalized inverse for the inverses on M by A and M by D yields the generalized schur complement. What is schur complement of Z matrix? Introduction. Schur complement is a very useful tool in matrix analysis. Another useful but less well-known concept is that of the parent complement of an irreducible non-negative matrix. The concept is derived from Schur complement and was introduced by Mayer in his construction of an algorithm for computing the stationary distribution vectors for Markov chains. If H is Hermitian and is either positive semi-definite or negative semi-definite, and if A is a non-singular principal submatrix of H, then the eigenvalues of the Schur complement H by A interlace those of H. As applications, we obtain the bounds for the minimum eigenvalues of irreducible symmetric Z matrix for the spectral radius of the adjacency matrix of a connected simple graph and also for minimal eigenvalues of the general Laplacian matrix of a connected weighted graph. For an irreducible non-negative matrix A, an upper bound for the maximal spectral radius of principal submatrices of a fixed order is given by Friedland and Nabian. In second half of section 4, we obtain a lower bound when A is in addition symmetrics. As a consequence, an upper bound for the minimal eigenvalues of principal submatrices of a fixed order of an irreducible symmetric Z matrix is also established. Example: AM inverse is equals to A inverse plus A inverse B into M by A whole inverse CA inverse minus A inverse B into M by A whole inverse minus M by A whole inverse CA inverse M by A into whole inverse. Then A power minus 2 is 0, 0, M by A whole power minus 1. That usualized to A power minus 1, 0, 0, D power minus 1. Preliminaries for the concept. Theorem A. Let A belongs to Lk, where K belongs to 1, comma 2, comma 3, up to so on n minus 1. And let A11 be a principal submatrix of order S, which is a non-singular M matrix. Then A by A11 belongs to Li A11 minus S, where I A11, the index of A11 in A, is defined to be the smallest positive integer I, such there is an I plus 1 cross I plus 1 principal submatrix of A, which is an no matrix and has A11 as a principal submatrix. Theorem B states that let A be an irreducible non-negative matrix of order n. Let phi is equals to alpha subset n. Then P of A by A alpha is also an irreducible non-negative matrix with a spectral radius alpha A. Moreover, if X is a positive eigenvector of A corresponding to rho A, then X alpha is a positive eigenvector of P of A by A alpha corresponding to rho A. As noted by referee in theorem A, one may replace the assumption A belongs to Lk, where K belongs to 1, comma 2, comma 3 up to so on n minus 1 by A is a Z matrix with non-negative diagonal entries which is not an M matrix. Also, it is known that if A is an M matrix and A11 is a non-singular principal submatrix, then A by 11 is an M matrix. So, theorem A also covers the case A equals to n if we adopt the convention IA11 is equals to n when A is an M matrix. Later in this paper, we will apply theorem A to E belongs to Lk for K belongs to n, with such understanding. Eigenvalues interlocking properties. Theorem 3.1. Let A be an Hermitian semi-definite matrix of order n, and let alpha be a non-empty subset of n, such that A alpha is non-singular. Then for any r equals to 1, comma 2, comma 3, so on up to n minus mod alpha, then lambda r a less than lambda r a by a alpha, lambda r a alpha, comma lambda r plus mod alpha a if a is positive semi-definite, lambda r a less than lambda r a alpha less than lambda r a by a alpha, lambda r plus mod alpha a if a is non-negative semi-definite. Proof. Let A equals to A plus 1 greater than 0 and let mod alpha is equals to K. First, suppose A is positive semi-definite. Thus, A and A alpha are both positive definite by the known fact that A minus 1 alpha is equals to A by A alpha minus 1, and the Cauchy interlocking theorem, we have that for any greater than 0 and s is equals to 1, 2, so on up to n minus k, 0 is less than or equals to lambda s a minus 1, less than or equals to lambda s a by a alpha minus 1, less than or equals to lambda s plus k into a minus 1. That usualized to lambda n plus 1 minus sa, lambda n minus k plus 1 minus s whole into a by a alpha, lambda n plus 1 minus s minus k a are greater than 0. Since the eigenvalues of matrix depends continuously on its entries and A belongs to A, where A by A alpha is belongs to A by A alpha, when a belongs to 0. We obtain lambda n plus 1 minus sa greater than lambda n minus k plus 1 minus s a by a alpha greater than or equals to n lambda plus 1 minus s minus k, where s is equals to 1, 2, 3, so on up to n minus k. So lambda r plus ka, lambda r a by a alpha, lambda r a, where r is equals to 1 comma 2 comma 3 up to so on n minus k. Since a alpha is equals to a by a alpha plus a alpha comma alpha a alpha minus 1a alpha comma alpha and a alpha comma alpha a alpha minus 1a alpha comma alpha is positive semi-definite by Welly's inequality, then lambda r a by a alpha greater than or equals to lambda r a alpha. So the first inequality follows. If a is negative semi-definite, then minus a is positive semi-definite. In addition, minus a by minus a alpha is equals to minus a by a alpha by inequality. We have lambda n plus 1 minus s of minus a, lambda n minus k plus 1 minus s whole of minus a by a alpha, lambda n plus 1 minus s minus k of minus a, s is equals to 1 comma 2 comma 3 comma 4 comma up to so on lambda minus k, where minus lambda a minus lambda of a by a alpha minus lambda s plus ka, where s is equals to 1 comma 2 comma 3 up to n minus k. By Welly's inequality again, we also obtain lambda r a alpha, lambda r a by a alpha. So the theorem follows. Corollary 3.2. Let A be an irreducible symmetric non-negative matrix of order n. Then for any phi is equals to alpha n, then r equals to 1, 2, 3 up to so on n minus mod alpha, there lambda r a, lambda r a alpha, lambda r p of a by a alpha, lambda r plus mod alpha a. Corollary 3.3. Let A be an irreducible symmetric non-negative matrix of order n. Then for any phi equals to alpha subset of n and r equals to 1 comma 2 comma 3 so on up to n minus mod alpha, then lambda r p of a by a alpha, lambda r p of a by a alpha into lambda r plus mod alpha minus mod alpha into p of a by a alpha. The bounds for eigenvalues of Z matrix. Theorem 4.1. Let A be an irreducible symmetric Z matrix of order n, then for any phi equals to alpha subset n, therefore 1 by bracket lambda 1 a alpha plus lambda 1 a alpha minus root over lambda 1 a alpha minus lambda 1 a alpha whole square plus 4 row a open interval alpha comma close interval alpha a into alpha open interval comma alpha whole power t less than or equals to lambda a, or less than or equals to minimum x alpha dot x alpha half of lambda 1 open interval a alpha plus lambda 1 I a alpha minus root over lambda 1 a alpha minus lambda 1 close interval a alpha whole square plus 4 into x power 3 alpha A into open interval alpha comma close interval alpha, where x alpha whole square, where the minimum is taken over all unit element vectors x alpha of A open interval alpha close interval alpha corresponding to lambda 1 A open interval alpha comma lambda 1 A close interval alpha respectively. Proof. Write A as Ti minus b with b greater than or equals to 0. Then b is reversible, reducible, symmetric. Rho b open interval alpha equals to t minus lambda 1 a open interval alpha, and the eigenvectors of b open interval alpha respectively b close interval alpha corresponding to rho b open interval alpha. Apply theorem 4.2 to B, the result follows. Theorem 4.2 states that let A be an irreducible symmetric Z matrix of order n. Let S be an integer with two Sn. Let alpha be a non-empty proper subset of n with mod alpha less than S. Then T of S of A is less than or equals to 1 by 2 T whole of Ts minus mod alpha open interval A alpha plus lambda 1 close interval alpha minus root over T of S minus lambda alpha plus A into open interval alpha minus lambda 1 into A closed interval whole square plus 4c 4c, where C alpha is equals to minimum beta subset n of alpha, where mod beta is equals to S minus mod alpha, maximum xt of alpha A, where alpha comma beta cross beta are Z matrix, and beta are respectively unit element vectors of A alpha and A beta correspondingly to lambda 1 A open interval alpha and lambda 1 A closed interval beta. Proof. Write A in the form Ti minus b with b greater than or equals to 0 for any phi equals to alpha subset n. Ps. B open interval alpha is equals to t minus t to s A open interval alpha. The result follows from theorem 4.14. Finally, we know that the bounds for the rho A is equals to rho n A, and lambda 1 A is utilized to tau n open interval A, as given by the theorems of 4.14 and 4.15. Agree with those are given respectively by theorems 4.2 and 4.9. Also, the inequality in theorem 4.14 holds an inequality for any choice of S and alpha if we take A to J. This is about the Schur complements of Z matrix. Thank you for giving this wonderful opportunity.